Thanks for having me here. My name is René Meyerhofer. I'm currently head of the Institute of Networks and Security at Johannes Kepler University in Linz. And I've been involved in the debate about secure messaging for a while. You could say that I'm getting slightly bitter because we keep having those same discussions year over year, depending on what the current political situation is. So please excuse a few snide remarks potentially because I've been having those arguments for so long. What I'm trying to do in the next roughly hour is to give a bit of an overview of the various different types of discussions that we've been having around secure messaging, and specifically the various different attacks that have been proposed or also pulled off against secure messaging apps. Why talk about attacking secure messaging apps? Because you may be concerned about some bad content that is being shared through social media or secure messaging, depending on however you define bad content. Of course, I would be remiss not to start with why do we think that this is really debatable? Because we've had those before. I mean, if you're concerned about what people talk about in secure messaging or social media, are you also concerned about what people talk about in real life, face-to-face, like behind closed doors? Is the next step asking for microphones in every flat, in every apartment? Because that's kind of the logical next step, which is one part of the slippery slope. The other part of that slippery slope for misuse that will occur if we have this kind of infrastructure is definitely the definition of bad content. What is bad? I mean, we can probably all agree that coordinating for terroristic attacks is bad, right? We can also agree that child sexual abuse material, CSAM, is bad. We don't want that. The agreement about, for example, Nazi material, that we have a pretty clear idea on National Socialistic material here in Austria and Germany is not universally accepted. So what is bad content depends on the policy of the day. And with or without an election, that can change very quickly. So all that I'm saying right now is any infrastructures that we build for surveilling data, surveilling transmission, surveilling secure messages in particular, will also exist after, for example, September 29. And whatever methods we have there will be accessible to whatever new policy we're going to have there. This is the misuse that I'm concerned about. But let's try to be systematic about it. So let's assume you want to somehow surveil social messaging or secure messaging apps on smartphones. What options do you have to do that? So the first thing is you can try to just look at the network. Don't touch the apps, don't touch the end user devices, don't touch the servers, just look at what's going on at the network transmission level, right? So very quickly, because I'm assuming most of you will be aware of that, I'm also using these kinds of talks for policymakers, so I do have a little bit of an intro of what actually happens with a secure messaging app. Please bear with me, I'm stepping through really quickly. If there are some questions, then please always don't hesitate to ask. So let's say you want to send a message with one of the social media apps from one device to the other. What actually happens? You write the message on one device, you send it to some cloud internet server that's out there, so there's a copy of that message on that server, and that at some point later on, the targeted device, the recipient, however you identify the recipient, probably by phone number or some other identifier, will go and fetch whatever messages are there for this target device, and then they also have a copy of that, right? This is how typically social media works. Now, if you have social media like, let's say, Facebook or X, Twitter, etc., however you want to call it, then you have a little bit more exposure because you send some, let's say, holiday picture towards that server, and it's not just one recipient, but it's like the world. It's many recipients. All your 327 closest friends will have access to that. And whoever else, when the policy on the server side is misconfigured or intentionally defaulting to public, will also have access to that. But that's maybe a side note. Now, there's a nice feature that, for example, also Facebook uses, because they also have those like buttons, not only for messages where you can have emoticon responses to whatever messages you send to each other, but also to posts. And probably you will know that those like buttons are actually small JavaScripts that are dynamically loaded from whatever social media server that is. So just by visiting that web page, if you're not like me and have an ad blocker, you automatically tell that social media service which web pages you visit, when and from which location typically. So there's a lot of data floating around that you may not intentionally be sharing with others in the world. But there are other services, like why does Snapchat, for example, exist? And why did WhatsApp pick from that feature of Snapchat? Vanishing messages. We've also seen that in the political debate in the last couple of days, where it's seen as a big problem if somebody sets a default timer for a message to, well, only appear for, let's say, 14 days and then auto-delete. Or why does Snapchat exist? Because it's the, I'll show you one thing, you show me another thing, and you only see it for a maximum 10 seconds. That's why the Snapchat app is in existence and why others have copied that. Signal also has the vanishing messages for slightly different reasons now. How does that work? You create a picture, you set a timer on the sender device, you send that to the server, and, and somebody picks it up, the recipient picks it up with that timer, and follows, honors that timer, and then only displays that message for 10 seconds or however long. Well, how difficult is it actually to modify the client, to ignore the timer? How do we know that the server ignores the timer and maybe doesn't store the content for longer than those 10 seconds? Direct answer, we don't. And yes, it's trivial to modify the client on the recipient side to not honor that timer. So it's really just a plea bargain. Please delete the message after 10 seconds. If you're nice, then you do it. If you don't, then yeah, well. But we have a different class of messengers. And this is what I call the secure messengers that are not just encrypted, because if you ask whatever vendor it is, they will all tell you, yes, of course, the data is fully encrypted, and they're not wrong, because whoever is not using TLS, HTTPS for the communication between the client and the server is doing it very wrong. So yes, there is, all that I showed you is at least traveling in an encrypted form over the network already. But that's terminated at the server side. And so the server has a plain text copy of that message. And yes, Telegram, for example, is encrypted, but only client to server encrypted for most cases. The secure messengers that I call secure use what's called end-to-end encryption, where the key material only lives at both endpoints. So there's one key that is used between the sender and between the recipient. And it doesn't matter how you transmit that message, if that's direct via Bluetooth or Wi-Fi ATOC communication or through an internet server, if you don't have the key and you use properly implemented encryption, then nobody can get at the content and your message is actually safe. Now, only the client, the intended client at the recipient side can actually decrypt it. Now, very short sideline. What is encryption? Encryption starts with basic symmetric encryption, where you've got the same key on both sides. You use that key on the one side to encrypt, on the other side to decrypt. And as long as you have a secure encryption implementation, like, for example, AES 128, not talking about post-quantum crypto here, let's say AES 128 is something that we all trust, then if you don't have the key, you're safe, then you can't, an attacker cannot decrypt it. Now, who's used a secure messenger and has actually exchanged a 128-bit key with the other side? No, that's very, okay, yes, very rare. It's not very usable. You don't have many friends who are prepared to do that with you. So there are other methods. We move on to asymmetric encryption, where you have a key pair, a public and a private key. The public key, as the name implies, you can share with everybody, with the world. And the private key you keep to yourself. You encrypt with a public key, you decrypt with a private key, and it works beautifully. That's not what we use in practice, though, because it's slow. It's about a factor of 1,000 slower than symmetric encryption, which doesn't matter much if you have 140 character long messages. But if you want to, let's say, send some video streams, if you want to have live video calls, it matters. So we have hybrid crypto, where what you encrypt with the asymmetric crypto primitives, you can only share the public key, you encrypt with the public key, everybody can know your public key. what you encrypt is not the actual data, but just a what we call temporary session key, and then you use symmetric encryption for the actual data encryption because that's much faster. So this is what we really use. Now, other question, that's kind of what we use for secure messaging at the moment. But has anybody verified the public key of the other party when you do that? Yes, a few people in here have. I have actually expected that. It's still very rare that you do that. And verifying a, let's say, 2048-bit public key, if you use RSA, or let's say a 256-bit or upwards elliptic curve public key, is still a lot of characters to read to each other. So there we come to the first question of secure messaging that I will briefly come back to later on, is how can you be certain that you use the correct public key of the other person? Because if you don't authenticate that, yes, nobody can decrypt it if they don't have the private key. But what if an attacker can give you another public key that you think belongs to your recipient person, but it's actually the one of the where the attacker has the private key, then you lose as well. The attacker can read your messages, can re-encrypt with the public key of the real recipient, and they can still do whatever they want with it. So it's important to authenticate it. And if you have a secure messaging app, like for example Signal, then for those conversations that actually matter to you, go to that small page, yes, it's a couple of clicks hidden, and read that comparison number that Signal gives you. What do they call it in the current UI? I forgot. That fingerprint of that key, basically. It's a little bit more complicated, but you can compare that if both sides see the same thing, then you don't have what we call a machine in the middle or on-path attack between those two. So that's when you become secure. Now, that's still not enough for secure messengers. If we talk about state-of-the-art of security, then we have something that's slightly more complicated. That's 1/3 of the top-level generic overview of the Signal protocol. And what you see here is that you don't have one public key per device, because it's pretty hard to keep one single key secret, the private part of that key secret, for a long time. If you use one key for, let's say, 10 years, the probability that one operating system or application bug will leak that private key is pretty high during that duration. So you don't rely on just a single public-private key pair, but with every single message that is being transmitted between those two parties, you actually create a changed public-private key pair. This is what we call ratcheting in those cryptographic protocols. Every single message transmission also adapts, increments, you could say, the evolution of those public-private key pairs. This is currently a state-of-the-art. And what that gives you is quite a few properties that we like to have from an end-to-end encrypted point of view, one being what we call perfect forward secrecy. So if somebody manages to break a key in the future, they can still not decrypt anything that happened before that. So your past is secure until the point when somebody cracks the key, when somebody gets the key through leaking or through maybe guessing it or cracking it with, let's say, quantum computers or whatever. Everything before that is still secure. And this ratcheting even goes further. It goes to what we call self-healing property, that when the attacker doesn't stay in the loop of that ratcheting and always stays in the middle, then at some point, a few messages in the future, you'll get to a state where both sides have a key that the attacker doesn't have anymore. So it's also self-healing in the sense of a one-time break will limit the time window where the attacker can get to the key material to decrypt it. So this is state-of-the-art. This is the Signal protocol. That is the namesake for the Signal messaging app. It's also supposedly used for content encryption in WhatsApp. I mean, to be honest, I believe that claim of the Meta company that WhatsApp uses that. I don't have any reason to not believe that, but we can't verify it. It's not open source. It's proprietary bits in there, so we can't easily verify. This is why I'm saying supposedly. There are other implementations that also use the Signal protocol. It has become popular. Why is the Signal protocol not used everywhere? One, the license is slightly restrictive for non-completely open source apps. It's a GPL license, and if you don't want to release under GPL, you have to buy a license from the Signal Foundation. So this is one reason why it's not in some of the other messengers. The other is that the Signal protocol still struggles with larger groups. So if you think about groups the size of Telegram, 200,000 people in one group. I mean, hint, hint, Telegram groups are not end-to-end encrypted, so they don't care about performance there. It's not their problem. But Signal groups, messaging groups with that protocol don't scale all that well. This is where, for example, the MLS protocol comes in. MLS has just, I think about 6 months ago, has finished standardization by IETF, and the MLS standard is roughly what the Signal protocol is doing, but in addition to that, having a strong focus on large groups, on group keying. If you really are into cryptographic protocols for secure messaging, read the MLS standard. It's a nice read, and it goes into all those threats and attack models. So MLS, I would consider the state-of-the-art protocol definition right now. It is an open standard. There are multiple implementations out there already. And for example, the Wire messenger that probably nobody uses, I've used it for a while, but it's fallen out of use, is mostly based on MLS. Others are beginning to look into or start adapting MLS. But those messengers that I list here, Signal, Wire, Android messages, the current one that's over RCS with end-to-end encryption is actually using a version of the Signal protocol. Maybe in the future with the iMessage interop, so iMessage and Android messages can talk over RCS right now, but not end-to-end encrypted. That's still being debated. Potentially that's going to also be properly end-to-end encrypted. WhatsApp presumably is. Threema uses their own homegrown protocol that nobody from the crypto community is really happy with, but it's also not obviously wrong. So Threema is a step down from Signal or MLS, but not obviously very bad. Threema is still in the category that I would consider a secure messenger. Telegram is not. Telegram does have the option of you go into the sub-menu and enable end-to-end encryption for some direct one-to-one communications. You have to enable that. It's not well done. There are many concerns about the protocol specification itself, and by default, it's not encrypted. And any groups that you have, groups or channels in Telegram, are not end-to-end encrypted, full stop. Matrix is in a weird in-between state. That OLM protocol is a variant of the Signal protocol. MEG-OLM is the one for the group keying. It's kind of okay-ish from the protocol specification, but there are quite some concerns about the specific implementations that float around in the Matrix ecosystem. So Matrix is good for interoperability. At the moment, I would not recommend it if you really require high confidentiality of your messages on the network. Now, this is only about content. This is only about the data that you send. Metadata is a different thing altogether. And there is that infamous quote by General Michael Hayden, "We kill people based on metadata." Metadata really just who is communicating with whom, when, how often, which types of messages, how many bytes, which time zones, etc., etc. Who is member of which groups, all this is metadata. And if you look at WhatsApp, as an example, as a very common, popular example, that supposedly encrypts the content well, but the metadata is all on the servers. Signal is taking great pains not to collect any metadata that they don't really need. So Signal is quite a step up when it comes to metadata resistance from all the others there. There are some really particularly metadata resistant messengers out there like Kutch and Briar and so on. The user base is very low, so if you use Kutch or Briar, I have them on my phone, I'm trying them. I don't have very many friends on those messengers, to be honest. So those are metadata resistant because they avoid unique identifiers that are directly personally linkable for the user accounts, aka the phone number. Any messenger that uses the phone number as primary identifier is problematic. That's one of my disagreements with Moxie on Signal. Their decision to always use the phone number is not one that I like, but it's currently the best that we have. And they tunnel through Tor mostly. So they avoid the network data analysis from the metadata point of view of who is communicating with whom by going through Tor. There might be a nice talk on Tor tomorrow. I think it's undecided, but it has been put into the system. Now, that is metadata, and just for all the messengers that are out there, metadata is really kind of open. Signal is trying not to collect a lot, but there is no real metadata resistance. That must be clear. But now, from the point of view of, let's say, a signals and intelligence service, they don't only want to get towards metadata, although the US and some other countries that we know of already claim that they kill based on metadata. They want to get really to the content. And a properly secure messenger doing end-to-end encryption makes it really kind of hard to get at the content just from network sniffing. So that option is out. If you want to get at the content for those messengers that I talked about, network is not enough. So can we look at the endpoints? Can we look at the clients themselves to get at the plain text content, at the text messages, at the images, at whatever is being transmitted between those social media clients or secure messengers? Because the endpoints need to have them in plain text anyway. Before encrypting or after decrypting, the plain text is on the client. Can we get at that? So let's look at that. Context here for the next couple of slides is Android, because I know a bit about Android. I've been full disclosure, I've been leading the Android platform security team at Google for 2 years. I've been leading the team that actually builds security measures in AOSP and the open source part that goes into the actual clients. I don't know a lot about iOS, so whatever I'm saying here only applies to Android, although from the distance, current version iOS and current version Android are very similar when it comes to the top-level security guarantees. So it should apply, but I'm explicitly only talking about Android because this is where I know what I'm talking about. The Android ecosystem is complex. There are many stakeholders, from the chipset designers, the Qualcomms and MediaTeks and Samsungs, etc. in the world, to the operating system manufacturer, which is basically Google, the fab that makes them. Then you have the ODM, the original device manufacturer. That is the one that actually makes the board, putting all those kinds of chips together. And then you have the OEM, the original equipment manufacturer. That's the label that you read on the box. There are many, many OEMs that don't have a fab capability or the capability to create their own boxes themselves. But there's just a few ODMs that make all the boards for a large number of OEMs who just slap the label on the box that you get in the shop. Then we have the app developers who ship some code, and there's some ODM and some OEM code and the operating system code, and from the chipset manufacturer code that all gets put together. We call that the system image that comes preloaded on the operating system, typically read-only. And the user installed apps, because a smartphone by definition allows you to install other apps on it, that will then combine to what you have on the phone and where you execute your secure messengers. Now, this is complex. There's a lot that can go wrong. There's a lot of players that can try to inject malicious code into that image. Keep that picture in mind, because I'll try to walk through a few steps where you could attack the endpoint and try to get the scanning done on the endpoint side. Now, the goal of securing that thing is to make it so secure that the team is not needed anymore. We are not yet there, and it will take a while to get there. But the goal is really to make it as tight so that this can't happen, that you can't have any attacks without the collaboration of the user who actually owns the device. Now, let's be a little bit more systematic. What is the threat model that we talk about here? We are talking about mobile phones. We are talking about mobile devices that can get lost, stolen, that somebody can get access to. So that we assume physical access, that an attacker can get physical access, at least temporarily, to your device. Kind of obvious, right? That an attacker can sniff on the network. Who is using the Wi-Fi here? Yeah, well, that Wi-Fi it's encrypted on the first hop. I don't know, I haven't checked who controls the next hop routers, so that somebody could sniff the traffic that you're creating with your device, and that somebody could temporarily access your devices for smartphones, kind of obvious, right? I mean, that's not a big surprise that we have this kind of threat model. However, we're talking about smartphones. So an additional threat model is that they execute untrusted code and they parse untrusted data. This is the very definition of a smartphone. You get somebody to get apps to install there. And many of those apps are not all non-malicious, so you have to assume that some of those apps will try to do something bad. It's part of the threat model. And additionally, and this is a little bit newer than the standard threat models, is we also have to assume insider-level attacks. We also have to assume that somebody who owns the signing keys, who can compile software for any one of those components, at the chipset designer, at the OEM, at the ODM, at maybe the operating system vendor, anybody with access to signing keys can be compelled or bribed or somehow gotten to get code signed with the proper keys and onto that system image. That's also part of the threat model that we have to consider when we talk about endpoint security. Now, there is a lot of thought that has gone into that, and there's an Android platform security model that has been implemented for a couple of years, where, for example, the first rule is you have to get consent by everybody, by the user who owns the device, by the app developer, and by the platform. And if any of them say no, then the action by default is blocked because that's a safer choice. And there's a couple of other rules, but the one that I want to deep dive on now, because it's important for secure messaging, is the rule number 5, that applications are security principles. And this is kind of surprising when you come from the typical standard desktop operating systems, where you have a user account, and that user account owns some data, and with that user account, you start some applications. And all those applications that this user account starts operate with the same privileges. If you start a PDF viewer, if you start a web browser with all the JavaScript that's going on in there, in both of them, if you start an image viewer, if you start a secure messaging app, if you start anything, whatever game that you downloaded from the internet with that user account, that application has full access to all the data that this user has access to. That's different on Android. Because here, an application and not the user account is what we call the security principle. This is where we align security policies with. Now, keep that in mind, because that is one of the basic rules of how those apps operate. Now, an app must be signed for installation on Android. Compared to other operating systems, there's not a lot of limitation. You can create your own public-private key pair as a developer. There's no limitations on how you create that key. You sign your own application, unless you use Google Play signing, then it manages that signing keys for you. But you can, when you install it through some other means, through some other channels, it's really the developer signs the app. It's signed, but there's no restriction on how it is being signed or which language an application is written in. It's a pretty open ecosystem. But there is what we call the application sandbox. So every application, every Android app that is being installed on the device gets, upon installation, a dynamic Android ID, an AID, which, if you're familiar with Unix concepts, the Linux kernel translates just simply to a UID. Every application I install gets its own UID, and that's very different to a standard desktop operating system, where all the applications that you start run with your user ID. So by default, within that sandbox, and that sandbox is actually enforced through DAC, discretionary access control, through SC Linux, mandatory access control, and is fairly tight compared to most of the other operating systems. When you install an application, this application only has access to its own data, and whatever other resources it gets to use based on the permissions that the user gives that app. But otherwise it cannot. So if you install one app, as the same Android user on that device, you install one app, you install a second app, they are completely separate from the operating systems, from the kernel's point of view when it comes to security policies. They don't have anything to do with each other. If there is no interface designed for those apps to communicate with each other, then app A cannot read the data of app B. Just not possible, because that's the security policy. You can have some shared files, you can have the downloads file, and you can have your images on the shared storage. That's explicitly shared storage that is accessible to multiple apps. But by default, when you receive a message in your Signal app, in your WhatsApp app, interesting wording here, then any other apps cannot read the personal files, the personal storage of those apps. So how do you actually get one app to scan what is in another app? In a smartphone operating system, that's not a thing, because that's not how the security policy is set up. That's intentionally not how it's set up. Because by having applications as security principles, what you don't have is something like a crypto Trojan that just goes and touches all the files that you own as the user, encrypts them, and sells you back the key for a few Bitcoin. You don't have that, because an app can only touch its own files, but not the files of any other app. What it also means is you cannot have an antivirus scanner or a bad content scanner that's just an app that you install on the device, and that can scan all the other apps, because it won't have the permission to scan all the other apps. Okay, so yeah, How do we do that? Yes, please.
Isn't that kind of counterproductive to backing up such a system?
Yes, backup is...
Security in FICO, right?
Yeah, backup is a bit of an exclusion, and we can have an hour-long separate discussion on the intricacies of backup. Yes, backup is hard. The default for Android backup is that when an app doesn't explicitly opt out of its own data being backed up, its own data store being backed up, then this is being included in Android backup, but this is end-to-end encrypted. So even Google, and yes, this is a very important property, Google does not have access to the encryption keys for the backup. It is stored on Google Drive, but encrypted so that it's also entangled with your so-called lock screen knowledge factor, the LSKF. If you don't know the lock screen knowledge factor, you can't get at the key. Yes, I know that skeptical look. A 4-digit or maybe 8-digit PIN doesn't have a lot of entropy. You can brute force that. So there's some server-side mitigation with secure elements that actually add some random salt to the key derivation function. And for getting the random salt out again, you also need to authenticate with your lock screen knowledge factor. And because it's in secure hardware, you can do some effective brute force slow down on that. So it's as I may, take an hour, talk to me later. I can talk to you about it for over an hour about just backup. But yes, backup is a bit of an exception of that model, and it's a tricky exception that needs to be handled carefully. But by default, no other app has access to any other app's data. You can't get at that. So how do we do that? We are still an intelligence service. We want to get at all the plain text data that has been sent, received through social media or secure messages. We can't get it through the network. We can't install an app on the device that will just scan all the other apps like you could do on Windows or Mac OS. You just get somebody to install an app, an antivirus app, and that has access to everything. And ideally, those antivirus apps even have a hook into the kernel, running kernel mode, and they can touch much more than the user can. That's not a thing on smartphone operating systems. There are no such hooks to do that. So how do we get into the operating system? How do we get that privileged level to do that scanning on the client side? Well, there are a few options. Let's look at the first option, which is really to somehow, because you need to modify the operating system to get in there, to get the privileges that the operating system normally doesn't give you. One is you could temporarily exploit a bug, a vulnerability in the operating system to get this kind of access. And this is really the kind of debate that we've been having right now for the last 2 weeks. Should we hack, attack, root, however you want to call it, the client devices to circumvent the security policy that is the default in those Android devices? Should we, as an intelligence service, hack those devices to break those security measures and just make it go away so that we can have our scanning in there? Let's step through that. I don't think it's a good idea. I have a few arguments why I don't think it's a good idea and why it's not a long-term plan to do this kind of exploiting of vulnerabilities for a long-term stable scanning approach. One is that you need to use bugs that are not publicly known, because bugs that are publicly known will get fixed quickly, however you define quickly, by the operating system vendors, and they will close down. Also, even if it's not just a bug getting known and fixed, just normal changes to the operating systems that happen all the time will lead to the exploit stopping to work. So it's a constant treadmill. You always have to find new bugs, you have to adapt. It's not you buy the attack software once and you have happy going for the next 5 years. It's a subscription model. And you always have to keep on top of that to get the new bugs. And this turns out to be kind of expensive because you need to pay people who know how to find exploitable bugs, how to write exploits for them to keep them up to date, and they also want to make a little bit of money, so you pay for that. It's not cheap. Second point is, in the US, a couple of years ago, there was that NOBUS statement that seems to be a thing in intelligence services there. It stands for nobody but us, and it's an illusion because they make themselves believe that they have capabilities that nobody else has, that only they can find those juicy bugs to exploit the operating system and break all the security guarantees. Short answer, it's not, and studies in academia and industry have shown that some of those bugs that are really interesting tend to be found by multiple teams. So there is a collision in the bug finding process. There is a certain probability that a bug that you found and that you think is 0-day has also been found by another team that's roughly as competent, and they're also using that. So by having those bugs, knowing those bugs, not making those bugs known to the vendor to be fixed, what you do is you leave the public that you're supposed to protect, you leave them open to be exploited by other players using those same bugs. Yeah, and, sorry, wrong button. And of course, the NSA and some other intelligence services in the world probably are sufficiently well staffed to find their own bugs and to write their own exploits. I somehow doubt that the Austrian intelligence service will, in the next couple of years, get a team capable of doing so. So the only realistic option to go that route is to buy those bugs, and you do that from the gray or black market, and that's not a nice one, because that's the same market that organized crime and all those political regimes that we don't really like in mass media or otherwise also use those same gray markets to buy their bugs from. So by paying into that market, you wittingly pay into the same market, you fund the same market that exploits bugs for purposes that we would probably consider to be criminal or at least politically unethical. You do that. That is the implication if you want to go that route of exploiting and continuing to exploit such vulnerabilities. So I would consider that not to be a really good option. Let's look at the others. You could try to modify the base image. How do you modify the base image? You get physical access to the device. That's part of our threat model. We assume a mobile device somebody will get physical access to. So somebody has the device, maybe very briefly. We still, in a kind of sexist way, call that the evil maid attack. You leave your device somewhere unattended in your hotel room. 10 minutes later, you have a slightly different operating system on that when you return, and you use that and enter your password on there. So that's one option that you could go. And well, what gets in the way is unfortunately code signing. Not only apps are signed, but also the operating system itself is signed. And it's turtles all the way down. So the apps are signed and the app signature is checked by the loader. The loader is part of the read-only system image. That read-only system image is checked by the kernel when it's loaded. And in newer Android versions, not only upon boot up when it's loaded, but upon every access in the block file system that is actually checked. Internally, it's pretty neat. It's a Merkle tree, so it's performant to check on access. And the kernel itself is checked by signatures, like turtles all the way down, is checked by the bootloader. And who checks the bootloader? Well, at some point there's a public key embedded into the actual ROM mask in the CPU. So it's an asymmetric signature checking all the way down the stack. Now, if you don't have one of those leaked keys, or if you can't break them, if the implementations of the signature verifications are correct, then what we call Android verified boot really checks the keys all the way down, and it's not really all that easy to modify the image on the device. I would say if in a correct current implementation, I don't think anybody has the capability to flash a new firmware on the device without you noticing. Yes? Thank you. So you don't do it behind, side question. Those signatures you can make verifiable. You can give an app access to check if the verified boot state is intact or not. Do you want to do that? Do you want to let every app check if the boot state of the device is the original one or has been modified? Pro, Signal can check if the firmware has been verified before opening it and warn you if the firmware has been changed because you might not have noticed otherwise. Con, your banking app might not run on your device if you intentionally run a customized firmware on the device. So, yeah, no easy answer. Yes?
And this also has the issue that the check might be patched out of the client side code. You need to check its server side.
Yes, exactly. You need some server-side inclusion in checking that, but it would still be the client fetching and what we call a key attestation certificate from Android key store. So at the moment, apps can do that. Apps can, for those reasons, I'm not saying if that's the right choice, but apps can query what the boot state is and have a cryptographic means of checking that going down to the security of the bootloader. If the bootloader is broken, then all bets are off. But as long as we assume the bootloader to be okay before it even passes control to the Linux kernel, apps can check their state. And yes, for example, the app Digitales Amt in Austria, which is our EID app here, has stopped working on devices with a custom firmware or rooted. I spoke to them. Now it's only a big fat warning that it displays upon starting. But if you click through that because you did it intentionally yourself, then you can still use it. I think that's a good compromise, to be honest, that apps can warn you, but let you click through if you want to as a user. So this is what I recommend apps do, to use that kind of Android verified boot capability to check if it has been verified and then just warn. Yes?
The bootloader already warns you if the bootloader is unlocked or you have your own custom signing keys.
Yes. So the problem there is, you're correct, the bootloader warns you, at least on Pixel devices. On other OEM devices, it's sometimes a different story. But if you intentionally unlock the bootloader to flash a custom firmware and you didn't flash your own public key and relock, which is something that's only possible on Pixels right now, unfortunately not other OEM devices, but you leave it unlocked, then the evil mate attack is a real problem, because then you don't know, because you always see that bootloader warning message, but you don't know if it changed behind your back between one boot and another. This is where verifying it cryptographically from the app point of view with the verified boot measures is actually helpful, because the app can tell if the underlying boot image has changed. So we are working on that to make that slightly more usable, but that's a paper currently being written. True, yes, very often the phone is not being restarted. I mean, at least it should be restarted on a monthly basis to apply security updates, so that's probably when you get it. But there are other reasons why it's still restarted. So it is an issue. But I would say that issue is small enough to actually be working with. But there was already that comment of, hey, why don't you do controlled market access? Why don't you effectively compel the OEMs to change the image for you, because they have the proper signing keys? Then you don't have to unlock the bootloader. Bootloader can be locked. You get the targeted over-the-air upgrade for those few devices, and they will execute the scanning app for you because they have been targeted. And the OEM has been legally told to do so and not talk about it. In some jurisdictions, that's possible. For example, in the US, vendors can be compelled to make some changes, whatever reasonable the changes those are, and never talk about it. So that's a thing. Now, that's harder, right? Because here the signature is correct and the verified boot chain is intact. We have something against that. It's called a binary transparency log. Because when you get every single image that is officially being released logged into an append-only public log, and no, it doesn't have to be a blockchain, it can be more efficient. It's again a Merkle tree. But you log that into a publicly visible and append-only log, then having that scanning functionality being injected into the base image, the attacker has two options. One, still do that, but then for the devices to accept the over-the-air upgrade when they check this kind of log, it has to be logged. It has to be in the publicly visible log, and the existence of that firmware, if not the exact details of that firmware, are in public knowledge. So the chance of getting caught is quite a lot higher. Or two, not log it, still sign the image, but not put it into the log. And then on the device, at the moment, bootloaders don't check, for example, those logs. That's maybe future work for bootloaders to start checking those logs as well. But the paper that we are working on would check those logs. For example, the pixel transparency log that exists is Pixel 6. So there is a public log of all the officially existing firmware images. With an app that uses the key attestation, you can actually check that. You can check if the image that has been booted on your own device is logged in that public log of those that should officially exist. So again, that's going away as an option. We are trying to lock down all those paths. This is not really open anymore. You could, of course, try to read the plain text off the device directly. Going back to the threat model, we assume physical access to the device, so we assume that's possible. Now, reading directly off the device, if it's turned on, there's that thing called lock screen. You have some user authentication, lock screen knowledge factor, the PIN code or password, biometry, or some lesser functions, and you need to know that lock screen knowledge factor. Now, that often gets lost in a debate. If an intelligence service has physical access to the device and can get the user to reveal their knowledge factor, they have all the data. They don't need any other tools. They don't need any hacking because they have the physical device. If they have the unlock key, if they have the password or PIN, they can just unlock the device and read everything off that device. And if it's really just going into the app and going through the screen and reading it off the screen, if there is no other interface to get it off the app itself. So that is still an option that's possible. But if you don't reveal the lock screen knowledge factor, tracking that in the sense of brute force, etc., that's really getting harder because on current generation devices, those are held in smart cards, and there's a brute force slowdown built into the smart cards firmware itself, and this is getting really hard. So of course, yeah, this is going back to certified hardware that is tightly controlled, hardware where you cannot flash your own parts. On that secure element that's on devices, you cannot flash your own firmware. That is for exactly those reasons, because this is the tiny little part that just really holds your crypto keys and that compares your PIN and password with before releasing those keys. So this is a compromise that we take from fully open and reflashable with custom firmware. On those small, tiny components, you cannot reflash. It's a compromise. It's not perfect, but as often there are compromises. Now, okay, we can't read it if the device is turned on and we don't know the lock screen. What if it's turned off? Can't we just boot a different firmware and read off the flash? Well, that used to be a thing, or desolder the flash and read it in a different device. That used to be a thing before encryption. Android 5 introduced full disk encryption. Android 7 introduced what we call now file-based encryption with slightly more granularity, where you have different encryption keys between different users and different profiles and so on. And this has become mandatory for all new devices shipping with at least Android 10. This was an achievement because, remember, some Android devices are sold for €100 or dollars or something. They don't really have fast CPUs, and this kind of full disk encryption slows it down. But this has been a process, and yeah, this was one of the achievements that happened, and it really makes a difference because you cannot just take a device that has been turned off and read it. So this is out, right? The conclusion that I draw is hacking devices is really getting harder, and reading directly off devices is not easy. Yes, please.
So you cannot easily read the disk.
Yes.
But you can maybe read the flash where the private key or something is stored.
Yeah, that's a point. If you really unsolder everything, read the flash, then everything there is encrypted, and where the key itself is stored, that's within the smart card. And those smart cards, if properly designed, are pretty hard to open up physically. Yeah. Yeah, the recall discussion is a tricky one. So if your operating system takes screenshots every 5 minutes or every minute or so, and somebody gets at this screenshot database, that's not good. So let's maybe not go there. I would consider that an anti-feature for some of those secure apps. Yes. Yes. So Android apps in their manifest can set the so-called secure flag, and then they are excluded from screenshots being taken. And as long as the Android system image is intact, it will honor that. And whatever service you have that takes screenshots, it will just be black. It won't get a screenshot from that app. So as long as the operating system is intact, that is kind of taken care of already, even with all those TeamViewer, etc., remote viewing apps that also use those kinds of APIs. So are all devices as secure as I have it in this list, thinking that it's pretty hard to do that? No, they're not. We are trying to measure that. We are trying to quantify how secure certain devices are. If you have a lot of Android devices in a in a test farm, please talk to us because we want to measure those properties on as many devices as possible. But that's a kind of side note. So back to the secure messaging. Seems that we can't really scan the app itself if the app is not collaborating. But what if the app is cooperating with us and we can get the app to do its own scanning? Right? That's still possible because the app can get at its own data by definition. So let's get the app to do its own scanning. That's the debate that we had last summer, to be specific. That is what was called client-side scanning. Let's mandate an app to implement its own filter to scan for bad content and block that bad content from being sent or received or displayed, maybe with or maybe without automatic reporting to the police if that filter hits anything that is considered bad. Now, technically, that's not that easy because how do you do the scanning? That's typically some kind of machine learning. And those all have errors. There's no perfect scanner that will only get flags for the bad content and not flag anything that's not considered bad. So in practice, you will get many false positives, and you will just overload any police forces with too many false positives, false matches that seem to be bad according to that filter, but are not really. And you just overload the personnel resources. So that's one. Then there's another challenge of how do you keep that secret? Remember, bad content includes, for example, child sexual abuse material. Stuff that can get you in jail just for possession. Now, if you can get that training or input material out of that filter, on devices that you ship in the field. So basically, WhatsApp has to ship a filter to detect material that is illegal to possess. Well, kind of hard, right? So you have to keep that filter secret, that filter implementation, non-extractable, which is hard. But even if it's not extractable, even if you can't just read the full machine learning model out of the device, there is a thing of extracting the training input if you just use it as an oracle. If you just give it some input, you get the output, and then you extract what it was trained with. Aha! You just shipped potentially illegal possession, illegal material to a couple of billion devices. Didn't people think about that? I'm not sure. So that was the debate last year. Then, how do you enforce that? How do you make people implement that filter? It's not as if it's so hard to create a secure messenger app these days. You download the Signal app source code off GitHub. Assuming that they implemented a filter, you just strip out the filter, compile it yourself, set up your own signaling server, and within your criminal organization, you have a perfectly secure messenger that doesn't use that filter. Done. How do you enforce apps using that? Not against the real organized crime. You can enforce that for the general population who doesn't go to compile their own Signal or WhatsApp client. But you cannot enforce it for actual organized crime. I don't see how that is supposed to work. And yeah, of course, it adds complexity. It makes the whole thing more complex, which itself adds more attack surface and makes the device, again, more insecure. Now, legally, that's also kind of hard, as the legal experts tell me, because there's that thing called mass surveillance for pre-crime scanning, which is actually not a thing in our legal system. And it also leads psychologically to self-censorship. We know that people who know that they are being watched behave differently. And this would create maybe a generation of youths under the perception that they're always under surveillance. That's psychologically not nice. Yes, please.
Something that also needs to be mentioned about filters based on machine learning is you need to have a training data set, which has interesting ethical questions.
Yes. How do you get the training data set? You get some organizations access to that training data set, and then you have to not have them reveal it. So those organizations you have to fully trust. Now, how hard is it for an organization that legally is not allowed to tell you what they train the model on because possession of that training material is illegal, to slip in some additional images that would also trigger the filter? To have not just CSAM material in there, but the tank man or other images in there that would also trigger the filter, and you could never tell because it's legally impossible for you to get the training data. Yes, I mean, will that remain secret? I don't believe it. The police doesn't want to do that because they don't have the personnel. They want to outsource that to another organization. Yeah, they all don't want to do that. So if you actually ask police organizations if they want to use that, if they want to have that client-side scanning, they will tell you no, because we know there are too many false positives. We don't have the personnel to look at all those false matches. You could build it into the operating system level. Yes, I have heard no consent so far from any of the operating system vendors to build anything like that, because it's not in the user interest, and they would not be popular for doing that. Oh, and yeah, all of that is under the assumption that you can get the most used apps to actually implement this enforced filter, right? Well, I got bad news for you. Signal and others have publicly declared that if that came to pass, they would just block access from the European Union. They would not implement that. Okay, so we just cut ourselves off of one of the most secure messengers right now because they would just stop operating here instead of doing that. Again, maybe that doesn't work that well. But why do I say that ML is not a good reason? Very, very brief, last couple of minutes into ML. What is machine learning? Just a very brief primer. Machine learning really is you have some input data and you want to get some decision from that input data. Basically, is that CSAM? Is that bad material? However your definition is of bad, or is it not? Previously, we had domain experts write some algorithms that take the input data, parse it, and make the decision in a very clearly formulated algorithmic way that we could understand how it comes to that. Machine learning splits that middle part into what we call feature extraction. So for example, if you do face recognition, you have some coordinates of your eyes, etc. Whatever features help you solve the problem, solve the decision, and then you have a classification or prediction that makes the decision. Now, you have some training and test data from which you extract the features and with which you train that classifier. And this training the classifier and then classifying, that we call machine learning. It's not much more than that. It's a statistical model that we create from data about how to come to a decision about some previously unknown data. There's no more magic in that. And if we don't manually get domain experts to write that feature extractor module, but when we learn that also from the training data, we call that deep learning. So that's the hype about deep learning explained in 30 seconds. How do you get all that data? Because to use deep learning effectively, you need lots of data. Why is deep learning now a thing and wasn't in the first or second hype cycle of AI? Because now we have the processing power and we have the data. Where do we get the data from? The internet. We get the data from all the social media, because this is a lot of data that we can use. So we get all the data from all those apps that I had mentioned before and dump it into the training and test data set. What is the quality of that training and test data set? If you grab it off Twitter, X, whatever, you make your own call about the quality of the training data. Now, if you use this kind of pipeline, there are many different places where data can leak. From the input, from the training, from the classifier, from the final decisions. And you can correlate any of those data leaks with other data sources that you might have lying around. So you would have to protect the whole pipeline for making those decisions. And that includes, for CSAM material, that includes the training data. That includes the feature selection or the deep learning process. That includes the model itself, because you can extract some of that training data from the model after you've shipped it. Now we assume, so that scanning, that client-side scanning assumes that you can protect the whole pipeline and you don't have any leaks in that pipeline. There's a nice web page there. Information is beautiful, that summarizes the largest data leaks in the last couple of years. You find all the big names in there, so what is the probability of not leaking any of that data? Again, I leave that call to you to make. Now, you have all that data, you do some machine learning, you ship that machine learning model into the client devices, and then you do it there. We don't end up with just data leaks, but you can also actively attack this whole pipeline because you can inject different input data. There's a thing called collisions. If you have a good classifier that is actually kind of good in detecting bad images and good images, you can, if you know how the model works, you can create images that look to a human user completely normal, completely innocuous, but explicitly trigger a decision flag here, trigger a false positive. So you send somebody an image that just looks like a funny cat picture because that's half the internet. It triggers their client-side scanning on the recipient, and it gets flagged for the police. Hey, there's some CSAM material on there. And then you have already a problem, even if it's untrue, because then the process already triggers. You can do the same thing at tweaking the model or just injecting something into training data. Remember where the training data came from? It came from the internet. It came from social media. So injecting something into the data that those machine learning models for client-side scanning train with is definitely possible. It's not a well-protected database that somebody runs where you have to do a Mission Impossible style hack to get some new data in the training data. You just post something on social media and wait until it's ingested into the next batch of training. So this, again, is hard. So, let's say client-side scanning is also tricky. Not a good way to go forward for scanning secure messaging content. Isn't there another thing that we can do? Blockchain, of course. In the last 10 years, it was always security is blockchain, right? You do blockchain. I haven't seen a good reason to use blockchain for that. But there's another thing why I say that blockchain, please don't, because look at the energy consumption. By the way, why did it halve here between 2022 and 2023? Because brownouts in China, there was so much Bitcoin mining going on in China that the electricity grid was overloaded. China kicked out the Bitcoin miners. They moved to, I think, Kazakhstan with the dirtiest coal that we have right now, but not as many, so it dropped. But even at current levels, this is Bitcoin, just Bitcoin, not all the other blockchains out there, just Bitcoin. This is Austria in total energy consumption. So all the electricity consumption, everything that we use in electricity, all that we use in here. So let's please not do that. And even if we don't consider all the electricity consumption that it has, there's rarely a good use case where you need to use this kind of proof of work blockchain. As I mentioned previously, that transparency log where you log all the firmwares that are out there is not one of those. It has completely different assumptions. So in most cases, no, you don't need it, which brings me to the end because I'm out of ideas on how to effectively do secure messaging surveillance. I don't have an answer for you. If you're an intelligence service who wants to do that, I can't give you any option that would actually work well in practice. Thank you.
So, vielen herzlichen Dank für den tollen Talk. Es gab hoffentlich viele interessante Zwischenfragen. Wir können gerne noch eine Fragerunde anhängen. Also ich kann auch gerne noch mal das Mikrofon reinreichen.
So let's try being productive and help our dear security agencies. Maybe they come up with a revival of the Clipper chip and then just decide, okay, if we compromise some of them, they'll realize in some kind of transparency log. Let's just legally force the vendor to compromise all the citizens, put some nice government-controlled vector, and then we will just decide who to compromise. Yeah. You think that idea might also, it feels like that might be an idea that could also pop up in the future?
I mean, it has been tried in the 90s. It hasn't flown then, but let's revive that idea. Let's give it a thought. I would have two reasons why I believe that's not such a good idea, because that Nobus that I talked about before, the nobody but us, it's an illusion. How long can even a well-financed intelligence organization really keep that one uber secret key that unlocks all the devices in the world? How long can they keep that controlled and secret? Snowden, I mean, yeah, secrets don't typically keep well. And the second answer is open source is kind of helpful there. If your whole operating system image down to the boot chain is open source and an intelligence agency really compels whoever controls the commit access to that open source repository to add some of those backdoors, then there is a chance that this will be spotted. It's not certain, because if you use memory unsafe languages like C and C++, that's one of the discussions that I really like having with Project Zero from Google. They are at a different level of attack. Their answer is a bug door, as they call it, is for them trivial to write. So something that looks like completely correct C or C++ code, but that they can dynamically exploit with high probability, is something that they could inject into the source code. So that's still possible. My answer to that is, yeah, okay, open source, good, because we have a chance of spotting such shenanigans. And please go away from doing C and C++, use languages that make it really harder to unintentionally write bugs in code, because that, I would argue, also makes it harder to intentionally write bugs that don't look like bugs. Yes, please. Yeah. I mean, yes, people have actually, during that client-side scanning debate, we have had those discussions of, let's not have one clearinghouse deciding what is bad content, what is CSAM, but let's have a number of them. And if two of them agree, then we really flag it, then it's bad. Or to have some crypto keys that are not controlled by one company or by one intelligence company, but let's have a bit of a mutually untrusting parties, a coalition of mutually untrusting parties that somehow collaborate to hold that all-encompassing unlocking key, or to have both of them have the capability. Theoretically speaking, from an academic point of view, that's a really neat idea. In our current global political climate, I just don't know if there would be any such group of states that would agree on any such scheme. Mm-hmm. Mm-hmm. Yeah. Yeah. I love risk 5. I would like to have, for example, future smart cards to be in risk 5, because it's simpler than an ARM core. Low complexity means lower probability of anything going wrong. And it's completely open hardware design. So for a very tiny component that doesn't need any performance characteristics, it's a nice basic design. I like it because it's completely open. Voting with 3 different implementations having to agree on something works well, for example, in avionics. The overall system complexity, however, goes up. And I would say having 3 separate implementations and 2 of them having to agree with a simple voter for the final decision works really well in stuff like avionics, where it's about safety, where you care about having a correct decision. When you move into the security domain with human intelligent attackers who try to exactly move into that weird state space of something that is not supposed to happen, changes the probability of outlying events. And then it gets really tricky. Pardon? Yeah. Agreed. So theoretically, I'm with you. I just don't believe that it will fly in practice. Yeah. And that's not even with active attackers. Yes.
You mentioned earlier about the self-censoring. That made me think about this content screening, you can't really adapt to fast-paced changes in lingo or hype of local lingo because you don't have the training data for that. That's one problem, and I already see that coming at the current generations of adolescents, young people, already have a special lingo developed to go around YouTube and Twitch content filtering. For example, a really known one is PDF file as a lingo for pedophile.
Okay.
And how do you match this with content scanning? You can't.
Yeah. Yep, agreed. So thank you. That's another argument why I think client-side scanning doesn't work. It's not just about the false positives, not just the false matches of innocuous content that is falsely triggered, but it's very easy to create content that is actually within the class that should be flagged, but that is not going to be flagged, which becomes a false negative. It's equally easy, but I think the much bigger problem from the police point of view is the false positives, because they're going to be overloaded. Their haystack is just going to be much bigger, and they won't find the real data in there. But you're completely right. I also believe that it would be sufficiently easy to tweak your content not to be triggered by those scanners if you know exactly how the model works. Yeah, fully agreed.
So something that I found missing from the slides is if the device is powered on but locked. There are companies like Celebrite who are advertising that they can still extract private data from the device through various exploits.
Yes.
And I also believe that with the smartphone, it's much harder than like a desktop computer, but the RAM content is still unencrypted, and the possibility of dumping the RAM content still exists.
Agreed, yeah. So Celebrite is pretty good at keeping up to date with exploitable bugs in the various devices. Celebrite is in that category of attack software that I consider, and it's expensive. They always have to stay on the ball to keep those bugs alive. They are still successful. It is still measurably getting harder to attack devices, so it is actually getting more difficult over the years to do so. And I fully agree that memory encryption, as is currently state-of-the-art for server-side CPUs, would be really nice to have. I just don't get it yet on smartphone CPUs. That's probably give it another 3 to 4 years for memory encryption to be a thing in most of the phones. It is more silicon, more power consumption, but I think we're moving that direction, actually. We're moving to full memory encryption. It's already in the current ARM standard, just not yet in standard chips.
I find it really interesting that Apple's M1 CPU chips, the memory chips and the CPU is on one...
within the same package, so
yes.
you can't detach them.
So,
yes.
So it also is a protection from memory contents being dumped.
Many of the current Android smartphone CPUs also have the single package DRAM plus CPU, so that's kind of thing. But still, you could, if you are quick enough, cold boot attacks, etc. There's a time window when you can still get the DRAM content after reboot. Memory encryption would solve that. Memory encryption with dynamic session keys created by the kernel for each of the partitions would solve that, but we don't have the hardware support for that yet.
So we were talking about a lot of technical details for the last 2 hours or so, I think. 1 hour.
I think it was a
sorry. Let's play devil's advocate for a second. You held this talk in a slightly different way, I assume, for policymakers.
Slightly different kind of talk then.
And let's assume that the police are actually as clue and helpless as they make themselves to be. So what would be your suggestion? What would your plan of attack for them be if you were in the lawmakers, the policymakers' position?
I mean, I can put myself in their shoes. I know that it would be nice for them to have this kind of capability, to just easily read secure message chats that are being transmitted, because that would make their life a lot easier. I can sympathize. It would also make their life a lot easier if they had a microphone in every apartment. Right? It would help. we might still not be willing to give them this capability. And I think here we are also on that line of there's too much potential for abuse of this capability. You should not have that. What can you do? If I give you that answer, you're not happy with me because you want to help people, you want to solve something, you want to solve real crime, so you're not happy with me. My answer would be standard police work will get you very far. Trying to get into those chat groups and reading those chat groups as one of the participants, I think, especially the intelligence services, the police, I'm not so sure about the legal perspective. You would need to ask some actual lawyers about that, but I'm pretty sure intelligence services are allowed to use pseudonyms. They're allowed to use false names to enter any groups and basically pretend to be somebody else. So just standard human intelligence police work getting into those groups and reading that would help you. And if it's some supposed attacks against concerts in Vienna being planned in unencrypted open Telegram groups, you don't need a lot of technical capability to read those groups. You just need the staff to do that. Best answer I could give.
So, question for someone who maybe has some insight into how Android gets onto like OEM devices. So when talking about messaging and like hardware security features, we always talk about pixels in iPhones, where it's almost kind of believable that those features work and are trustable. But if I go into a supermarket and buy some Alcatel 3x rebranded phone for 20 euros, how true is any of that still?
The honest but maybe slightly depressing answer is, if I was a journalist or somebody who had to hide from the current government in my own country, I would not use a sub 200 euro phone at the moment because many of those guarantees just don't hold in practice. I mean, the same Android security model is there. They also have kind of the same basic hardware capabilities. They might not have the secure element to store your crypto keys and to do the PIN and password verification. The problem is that the cheaper OEMs, the cheaper manufacturers, they have to cut corners somewhere. So they have hardware that is probably about 10 years old from the design point of view of the main CPUs. They use cheap designs for attaching the DRAM, etc. So they have to cut corners everywhere to get that price down. There are probably known attacks in the old hardware. They might not have the security team to get the kernel updates all there, to quickly get all the Android system security fixes into their devices, etc., etc. There are some answers that are around what we call GKI, generic kernel image, GSI, generic system image, so that an OEM doesn't actually nowadays need to do their own customization of the Linux kernel or the basic Android system image anymore. They only have to provide some of the hardware drivers required for that specific board. It's been a process. Not many OEMs use those generic images so far because they would be updated by Google automatically and they get the patches as quickly as the pixels do, the security patches. That is a bit of an ecosystem impact on how quickly will they adapt. Again, economy is hard because how does an OEM actually sell a device for, let's say, 100 euros or in some regions 50 euros or below, and that still have a phone that has comparatively amazing computational capabilities and really does a lot because they add some bundled adware on top. They get paid to add some software into the system images. It's an economic model. They get paid to add the Facebook and other apps in the base image and be pre-installed there. And this is why the device costs less. So it's a bit like an ad-funded phone. I'm not judging that. It's just the realities of economy. And so this is one reason why those manufacturers currently are not really fond of not rolling their own system image because then they lose some part of their income. But there are some trends on how to solve that problem. They will just take a couple more years to actually come into the mass market.
Also from experience, just having one of those systems that have like the generic system image or whatever, this doesn't mean that updates don't stop after 1 year.
Yes. That is another thing where there's at the moment a really big gap between the different price levels. If you have some of the flagship devices of the big names, then at the moment, and this is new and this is great, you get a guarantee, at least self-guarantee by the manufacturer, that you get 7 years of security updates. This hasn't been there for the longest time in the Android system, and I'm so excited that this is finally happening. But you only get those 7 years for the flagship devices. It will get into the market. So in 5 years down the line, we will probably see that as a standard, but we don't see that right now, which is another reason why you shouldn't use a really cheap phone, probably if you don't really know what you're doing. You can buy cheap hardware and flash something like Moreno, LineageOS, GrapheneOS, etc. on there, keep it updated yourself. Make sure that you maybe ideally compile that yourself, because a LineageOS port compiled by some random person on the internet and made available is maybe not the most trustworthy per se. So if you get the source, compile it yourself, and really know what you're doing, you can use cheap hardware with up-to-date software. It's not something that most people would do. So to really get the security, all the current security that I'm assuming to be there, unfortunately, it's flagship devices right now. In 5 years, it might be all the mid-range and maybe a few of the low-range as well. Yes?
Yeah, going a bit, like you were talking a bit about Signal, and you said Signal is doing great steps to not collect metadata. Is this something we have to trust, or can we verify?
No, you can't verify all the Signal server implementations, unfortunately. So Signal, for some of the matching that they have to do, so there is the keeping your phone number as identifier assigned to yourself. There is the matching, like who in your contact book also uses Signal, so you can contact them through Signal, which basically means uploading a little bit of a derivation of all the phone numbers that you have in your phone book to the Signal server. They do some server-side matching, and because they don't want to have that data lying all around, because it's a liability for law enforcement requests, they do this kind of matching in SGX enclaves. Yes, groans in the audience. We know that SGX is not particularly secure. I know that as well. I'm not a fan of SGX. They're trying hard. It's not perfect. And at the moment, as to the best of my knowledge, I do not think that they have enclave attestation enabled. So I do not think that the standard Signal client or another software could remotely verify that those enclaves are running that exact correct software. Besides that, I don't think that is all open source anyways, because SGX requires Intel SDK to write something that can go into the enclave. Yeah. You still need to trust Signal. You also need to trust the Signal Foundation not to mess up the client source code. But at least they're trying hard to not collect anything or store anything that they really don't need, which is more than most of the other messengers. I mean, I haven't really talked too much about Briar and Kutch and so on. They don't have anything because there is no central coordination server for those. But again, the usability for Briar, Kutch, and the others hasn't been addressed. As mentioned, I have them on my phone. I have 0 friends on those at the moment. So, yeah.
So, thank you again very much. Please give him a warm round of applause.
Thank you.
Dankeschön.